Hi there, this is Mr. Sand, and we're going to talk today about a new unit in circular motion. This is Unit 5. And this first topic in this circular motion unit is called center-seeking acceleration. Okay, this is a little bit weird, but I want you just to think about a bowling ball. I often do this, and you can do this with any kind of ball that you have maybe laying around. I don't know if you have like a basketball or a soccer ball or something like that. But let's just say that you've got this ball, and there it is, and this is from a top-down view, and the ball is moving just straight, just going along, going along, going along. Now, if you want to then move this ball into a circle, so it's going straight like this is showing the motion, it's not the force. What do you have to do? Let's say we wanted to rotate in a circle around a point like that. So let's say that we wanted to rotate in a circle, kind of like, oh, that's not a circle. Okay, eventually it'll get to a circle here. I guarantee it. Like this. We want the ball to rotate around and around and around at center point. How are we going to do that? If you try this with like a bowling ball that has lots of mass here, you'll find that every time you want, let's just say you have to tap it, all right? Like you can't hold this ball in this circle like this, but if you tap it, you're actually going to be applying, and this is weird, you just do this unconsciously. You'll be applying force, if we just tap it, you'll be applying force towards the center every time you tap the ball. I do this demonstration all the time in class. Every time you tap the ball, you'll tap it towards the middle to keep it going along that circular path. So to go in a circular path, guess what you need? You need a force keeping that object going towards the middle every single second, every single half second, every instant. This thing has to go towards the middle. It's weird. It's not how you normally think of how things work, but it's true. You can do this with, let's say, like a string. If you've got a string, let's say this is a center point, and you're whirling something around your head, you need a string. And here's a ball. Let's say that's a ball. It's attached to that string. If you are whirling this string around your head, going around, around, around like this, okay, you're going to need a force. I'll draw a different color for the force. A force. Notice what you're doing when you're pulling a string. You're pulling the ball towards you. So you're applying a force at every instant along here. You're applying the force. You're applying the force. Oops, it should be pointing towards the middle. You're applying the force towards the middle. So this force you're applying towards the middle, that has a special name. And it's not what you think it might be. It's centri, which means central. And then the last part of the word is pedal, or centripetal. That's how you normally pronounce it. It's a centripetal force. It's the force towards the center. It's a center-seeking force. Center-seeking. This is not centrifugal or centrifugal, as some people like to say. Fugal means to get away. This is fleeing force. It's not centrifugal. It's centripetal. This is the force that's pulling something that keeps it going along the circular path. There's always a force going in, going in, going in, going in, going in, going in. Now you can use a string. You can use a barrier on the outside. Let's say you have just let's just say you have like a barrier on the outside of this, a loop that keeps it from going outside. Now, let's think about what happens if you cut this string. Let's just cut that string. You're flinging it around, flinging it around, flinging it around, and all of a sudden you cut the string. What will happen to that ball? Well, that ball will go flying off, and according to Newton's first law, that ball will go flying off straight, and a straight path. It'll be going just like this. If, let's say, you cut it at this instant, it'll go straight, fly off, and that towards that path. You should take a look at, and I'll post this. These Olympians, they have this thing called the hammer throw. And the hammer throw is just this. It's a big ball, and it's attached to a string, and they whirl around, whirl around, whirl around, and then they release. They release that ball and they make it, they throw it. They release at this point, they throw it, and this ball goes straight. It doesn't curve. Some people think it curves off like this. Some people think it curves off towards like this, but it goes absolutely straight. And you'll see that. I'm going to show you some videos of that. Other things that are cool related to this are like a roller coaster ride. No, not a roller coaster ride. Yeah, actually a roller coaster ride. So let's say you're having like a loop in a roller coaster. It goes like this. And you're this little person right here in the roller coaster. Hopefully not standing up like this little stick person is. Well, if you're on this roller coaster, this track is providing the force that's keeping you going along the circular path. If you didn't have this track, you would just go flying straight off. You'd be going straight off. But you do have that track, and so that's going to keep you on this circular path. So we should talk about a formula here. We're not going to derive this formula, but I'm going to just tell you what it is. There's an acceleration that you have when you're moving around in a circle. It's a center-seeking or centripetal acceleration here, and it's just this. It's in your workbook. All it is v squared, which is the velocity going around, divided by r, which is the radius of a circle. So the velocity, this is the velocity that you have, the instantaneous velocity at any point along here. That's the velocity. And r is the radius from the outside to the center of the circle. So that's our acceleration towards the middle. Now, I give you a warm-up problem. Let's go through a couple warm-up problems here. It says, 1, when Dale drives his race car around a perfectly circular track, his speedometer reads a constant 212 miles per hour. However, he's accelerating. Explain why he's accelerating and in which direction he's accelerating. What you should say here is that he's accelerating because he needs to stay on that circular path. So at every instant on that circular path, he is actually accelerating towards the center, towards the center, towards the center, towards the center. He's accelerating. And he's also got a force that's related to that acceleration. That's always pushing towards the center. The track is actually providing that force, and friction is providing that force. And gravity is providing that force. We'll see in a couple examples, a couple challenge problems like that. So that's how he's accelerating, and he's always accelerating towards the center of the circle. That's warm-up problem number 1. Number 2 says write a formula for centripetal force without using the variable for acceleration. Centripetal force. Centripetal force. So we know from F equals ma, that's praise Newton, second law right here. Well, that's a force equals mass times acceleration. If we use this formula here and combine it, let's say we plug this into the A right here. It's a very, very simple derivation. You should be able to do this on your own, but I'll just do it right here. So if we plug the A in, it's going to look like this. mv squared over r. This equals centripetal force. I'll put a little c underneath to denote that it's centripetal. So that's our formula for centripetal force. Okay, 3. Calculate the amount of force necessary to keep a 2-kilogram tetherball moving at a speed of 6 meters per second in a circle of a radius 1.5 meters. So we know a couple things here. This is for problem number 3, warm-up problem number 3. We need the force, so we're going to use a centripetal force. We're going to use this equation right here. We know the mass of this ball. The mass of the ball is 2.0 kilograms, and we know the speed. We know the velocity. And we're just going to assume that velocity stays the same, so it's 6 meters per second. Great. So all you do is you plug these values in here. Oh, and what's the radius? Radius is 1.5. This is a super simple problem. So this is exactly this problem right here, this formula right here. So I'm just going to plug in. I'm just going to plug in those values. So it's going to be FC equals 2 kilograms times v squared, which is 6.0 meters per second. This whole thing squared all over 1.5. So I put that in my calculator. It's going to be divided by 1.5. You should get 48. That's the force. And what's the force in? It's in newtons. So it's going to be 48. We've got 2 sig figs. So that's good. All right. I hope you learned something. And check out the videos. There's going to be some awesome videos that are also taking place in the space station. That's it for me. Good luck with the problems.